introduction. So hello everyone. So welcome to attend our this week Progress in Efficient AI seminar. And today we're very glad to have the Dr. Chaoyang He from the FedML to give this talk on the federal learning. And Dr. He is currently the co-founder and the CTO of the FedML, and an AI company running for community connecting and building AI from anywhere at any scale for developing the marketplace, ML Ops, Edge AI SDK, and open source library. And Chaoyang received his PhD degree in computer science from the University of Southern California. He also worked closely with researchers and engineers at Google, Facebook, Amazon, and Tencent, those big tech companies. And previously, he was a research and development team manager and the principal software engineer and the Tencent team leader and the senior software engineer and Baidu and the software engineer and Huawei. And his research focus on the distributed federated machine learning algorithm system and applications. And he has received a lot of the awards, including the Amazon ML Fellowship, Qualcomm Innovation Fellowship, Tencent Outstanding Staff Award, WeChat Special Award for Innovation, and so on. And he has published papers at ICML, NURBS, CVPR, ICLEAR, AAAI, MLCs, NACL, among others. And beside pure research, he obtained 3 years of experience in the R&D team management and Tencent for internet products and the business. And now let's welcome Chaoyang to give this talk, Federated Distributed Machine Learning at Scale from System to Algorithm and to Applications.
Okay, so, hi everyone, thank you for the introduction. Such a long introduction, seems I'm too old compared to some young graduate PhD students. Yeah, so today my talk is about federated and distributed machine learning at scale. From systems to algorithm and applications. So it's an end-to-end research style. It covers online system design, especially distributed system, and also some machine learning and security algorithm. And finally, I will briefly talk about some applications, especially in computer vision, large language processing, and graph neural networks. Yeah, so from this figure, you can see that my research start from distributed training on multiple GPUs, and then I switched to federated learning on edge devices. So distributed training happens a lot in industry. When I was working at Tencent, we are building some distributed training infrastructure, but after working at USC as a PhD student, I mainly focused on federated learning. And recently we switched to, we call it social and decentralized machine learning. So it's the rightist figure showing that people can collaborate using their private data in a marketplace. So you can see these three are very coherent and relevant areas. Both are in the intersection of distributed system and machine learning. So that's my focus. We can call it machine learning system. Yeah, so next, so I think you already covered my background. So today's talk, I mainly, sorry. So as you can see that machine learning is a very large scale problem. When you look at from the optimization perspective, so this is the basic optimization of machine learning problem. So it means you want to minimize the loss, especially the cost function in many samples. So from the sample perspective, so now the machine learning is a very big problem because it involves huge number of data points. And from the optimization perspective, you can see normally it involves some long-convex optimization, especially for neural networks, and weakly supervised, meaning that you may not have enough labels in your program. And it also dynamical, meaning that the data distribution may evolve and your loss function may not cover the dynamic distribution. And finally, the model size is super big, especially you can see nowadays transformers has already make the model size to billion and even trillion level number of parameters. So in order to address this large scale machine learning problem, people start from 10 years ago. You can see the breaking through of ImageNet is that it make researchers understand that data is important. you need more data and bigger model to get a good performance. So at that 10 years ago, you can see people use 2 GPUs. It's still parallel computing because it has the inter GPU and the inter GPU computing to hold this AnnexNet so that it can train on this image net task. And at that day, it's a very big task, but nowadays you can see people already generalized this idea to AlphaGo, AlphaFold to biology, and even GPT-3 for natural language processing. All these are breaking through in AI. But the issue that you can see the modern AI is a combination of big data, which involves TB or PB level storage and huge compute because it requires thousands of GPU to finish the training, especially for GPT-3. Like yesterday, you can see Meta published OPT, which is a public giant transformer models for natural language processing. So the secret of this kind of model normally involves thousands of GPU training a few weeks. And also you can see the model size is super big, like a massive model size, like billion level transformer models. So last infancy of this deep learning. But the issue is that you can see these tasks are all based on public data. So what if we don't have public data? How we can train such giant model? This happens a lot in practice, especially starting from 3 years ago when I started my PhD. I find this is a key problem because at that age, we find many scenarios we don't have enough big data to train a good deep learning model. For example, you can see GDPR from Europe and CPRA is California Private Right Act. Especially in California, it's hard to collect data, especially from your smartphones. And also in some cases like commercial interest. For example, if you have some wet experience in chemistry, biology, such kind of experience that, for example, you label some molecules, it's very hard to share this commercial interest to other companies. But normally a single company cannot train a giant, a good model. So this data isolation is also happens in this scenario. And the third setting is also interesting. You can see autonomous driving because it generates 4 gigabytes, for example, 4 gigabyte data per day. And even in satellite, which is an interesting case we collaborate with Microsoft recently. We find that high communication cost is also bottleneck because the satellite cannot transform the high resolution image to the ground Earth, like the Earth station, because satellite normally has very limited communication bandwidth with the station, although it has high bandwidth across different satellites. So these are all the scenarios that people cannot train, cannot centralize data. Another setting is also very interesting, which is actually the main focus of our company. We want to do Web3, which is a decentralized internet, meaning that people's data decentralized, is not controlled by Google or Facebook. And people can train this data by, for example, based on blockchain. And you can train your private data and share your private data. But how people can directly share this data, I think their first key step is called federated learning. That's why our research mainly focus here. So federated learning can solve the previous data isolation problem and also the data market problem. So we hope that data can be shared, but never can be copied to others. So you share securely and people can use your data training model, but they cannot see your data. So that's the vision of our company and our research. So you can see that diverse applications can use this paradigm, especially this machine learning, distributed machine learning paradigm, like the healthcare. For example, you can train some X-ray image segmentation by using data from many hospitals. And finance, for example, if a social network company can share some profiling for this financial company to boost the performance of the fraud detection, for example. And for retail and smart home and smart city, you can see there are a lot of smart cameras and autonomous driving, and even VR, you can protect your eyeballs interaction with VR device. So that's also kinds of privacy. So there are tons of application drives us to develop this direction. So since I guess maybe this seminar, people need to, you may need some background about federated learning. So let's start from a basic formulation. So federated learning normally start from the server side. So the server directly synchronize the model to the client side. For example, I send a W to the client side. So each client can train this W, the model, based on its private data. The training method normally, for example, the SGD, stochastic gradient descent, or some advanced SGD optimizer like ADAM and SGD with momenta, which is common practice in deep learning. And then each client can synchronize the trained weight to the server side. And what the server side does is that it tries to aggregate the weight. For example, the WT plus 1K, meaning that we want to summarize the K workers' weight and then do a weighted average. So here, the weighted average is based on the number of samples on each client, and then we get WT plus 1. And then we can synchronize this WT plus 1 to the client side, and then start another round of training. So essentially, this process is that we train locally and we aggregate globally. We train locally, the benefit is that we don't need to move the data to the central server so that it can break the constraint that I mentioned, like the privacy, communication cost, and commercial interest, for example. And we aggregate globally, there's a benefit that we can also protect the individual privacy because we can use some skill aggregation measure to guarantee that the server cannot see an individual weight. We can only see the aggregated result. So that's why this pattern, this algorithm is so promising in practice. So there are a lot of benefits to address the constraint I just mentioned. So on the left figure, you can see there's a very simple example why this it can work. For example, you want to type a lot of language with, to chat with your friend, there are a lot of privacy there. So using this method, you can train a language model that's without disclosing your private data. So that's the benefit. Yeah, so based on this formulation, you can see there are a lot of issues and challenges to make it perfect in real world. So first, you can see the data is in each kind may be heterogeneous. For example, your behavior of typing the chat with your friends and the language you use, although we both speak Chinese or English, but language is quite different. So, and also the behavior and the frequency of talk is different. So that's we call it data heterogeneity in each kind. And also for this red color, you can see we want to train a model locally, meaning that the performance of this device may not be enough to handle this model training. For example, maybe the memory is not enough to hold a transformer model, or maybe the training speed is too slow that you cannot wait a few months to finish the model training. So there's some resource constraint problem here when you do local training. And also when you return this W to the server, there must be some challenging, like for example, some guy may try to attack this model so that it break your accuracy when you're training. It may downgrade your accuracy. So how to guarantee the privacy and security for this W when you transmit back and forth between the client and server? That's also the problem. So based on this formulation, now you can see that federated learning is very diverse and research area. It involves a lot of research problem, and even as Professor Yuan just mentioned, maybe in system constraint wise, we can see some hardware improvement. So from statistic challenges, as I just mentioned, it mainly happens in non-ID problem. And recently I also work on another interesting problem like unsupervised and weakly supervised learning, means that in your edge devices, you may not have enough resource to ask your users to help you to label the data, because users normally are very reluctant to label their own private data. And also continuous learning is very important for, especially for product, because as your product runs on the smartphone users, data distribution always involves a lot, meaning that today you train the model, you get good performance. Maybe next month the performance becomes worse. So you have to upgrade your model and do some retraining or fine tuning to improve it. So that direction we call it continuous and meta learning. And for trustworthy, as I just introduced, it's more about how to make it secure and private, especially for the model and the data, to avoid the people can inverting model to get the raw data. So that's some research question there. And for system constraint, as I just mentioned, it's more like improving the communication and computation efficiency, and also how to support multi-tenant federated learning on cloud computing. So it also involves cloud computing a lot. And recently in our company, we developed a ML platform, a cloud computing platform to support federated learning. I think later I will introduce that system. And for application level, you can see federated learning is not a specific application. It's not not a specific algorithm. Actually, it's a very underlying infrastructure that has to support diverse application. Nearly all AI applications can be federated. So that's why we also need to do some research especially in computer vision, natural language processing, and data mining. So now, as you can also see that the value of the research community, it involves all the AI community, like the New York's ICML and the iClear, MLCs, and some CVPR and ACL. Almost all the conferences are talking about federated learning. So it's a very hot topic. Last year, it has about 10K publications. Yeah, even bigger than reinforcement learning in AI community. So in our research, especially in our lab at USC, we mainly target 3 problems. As you can see, there are tons of problems to work with, but we mainly focus on these 3. The first one is the fundamental algorithm, like how to do heterogeneous and unsupervised federated learning. And also how to address the resource constraint, because we focus on edge devices like smartphones and some resource constrained edge servers on some hospitals and banks. We hope to do some training and accelerate training there. And also especially in skill aggregation, because this is a diagram that's quite different from differential privacy in federated learning. We hope that the global aggregation can be scaled to individual models. So we mainly push for this direction rather than differential privacy. So that's a flavor of research in our lab. So today's talk, I mainly start from the system-wise and then go to algorithm, and then finally talk about a little bit about the application. So the next slide is the FedML library. So it's developed almost 3 years ago, because at that time we don't have any library to do research. Although there are some libraries at Tencent and WeBank, we can do financial industry federated learning, but for research-wise, it's not friendly to researchers to try different ideas. Especially at that time for our lab, we have 10 PhD students try to focus on this area, but there's no such a library to try new ideas. So at that time, we tried to finish this library. So first, let me introduce this library and talk about some research based on this library. So this library lies in the online ecosystem and the infrastructure to support different algorithms and then go to application. This library want to solve such kind of challenge. First, we want to support diverse platform. As you can see on the right side, researchers mainly focus on standalone simulation. But in industry, people focused on distributed computing on real devices like your edge server or smartphones like Google's Stereo. So the research gap is that researchers cannot scale up to large-scale real-world system, or they try some standalone simulation, but they don't know what's happening in real world. Or in real-world setting, if you want to try some advanced algorithm developed by researcher, we have to port such standalone simulation code to real-world system and then evaluate it, which is a long engineering process with a lot of effort. So our library try to focus on here and try to bridge this gap. We hope people can write once, for example, you just write a standalone simulation code, and then you can migrate it to a distributed computing setting. And the second challenge, we also find that's very important, because federated learning is not just a centralized topology. It also involves some different communication topology, for example, decentralized network like social network, and also some cases that people do not hope there is a central server to control the aggregation. And hierarchy also happens a lot in wireless communication. For example, we can deploy an edge server in a special city and then do aggregation in that city and then aggregate it at a state level. So it's hierarchical distributed training. And also we consider vertical federated learning, meaning that different organization has different feature space. So by that way, we can try to combine the feature space from different area, different organizations, and also including speed learning, meaning that two organizers or two person and devices can collaborate training this model. Each device is hold part of the neural network. So there are tons of different distributed training paradigms for in this setting. So we hope to support all in our library so that people can try different ideas in different scenarios. So currently, federated learning in industry mainly focus on the first centralized communication pattern and the vertical federated learning for financial industry. And for speed learning, it may be used for some resource constraint setting. For blockchain, it's mainly focused on decentralized. So all this has some special demands in practice. And also, we hope to compare some baseline. So this is a common practice. If you want to build a library, you have to provide some benchmark result for researchers to refer and compare with other organisms. So that's the motivation, and we hope to write once and scale your code to distributed training and even urge training. So the code is very simple. You just initialize your device and load the data and create model and then just start train. So recently we have reorganized these APIs and try to even make it simpler. And you can check our GitHub to see the latest code. So this is the old version that I published almost 2 years ago. And as you can see, there are a lot of algorithm support and models and datasets. And so this is the architecture overview. As you can see on the left side, on the lowest side, we have the distributed communication backend like MPI, MQTT, and even RPC, especially gRPC and PyTorch RPC for intra-cluster training. And based on this communication pattern, we have some security and topology management, like different topology I just mentioned, and also security and privacy primitive APIs so that you can do some differential privacy through aggregation. And on the right side is the training engine. So although you can see currently we are based on PyTorch, but actually in our company, we are trying to develop a C++ and even Rust programming language. I'm not sure whether you heard about Rust. So it's very memory efficient programming language that can support edge devices training. So hopefully our company can be the first one to finish the library for federated learning. So that costs a lot of engineering effort there because we need to redesign the training engine. It's not like PyTorch. It's very similar like 5 years ago. If you look at Yang Qin. So Yang Qin is Alibaba VP. Previously, actually, he's a researcher at Google TensorFlow and Cafe 2, and then migrated to PyTorch. So at that time, we even don't have a deep learning library. So now federated learning faces the same problem, and we even do not have edge devices training engine there. So if you use PyTorch training there, the memory cost and the efficiency there is a big problem. So that's why we focus a lot there. And on the middle layer is some unified APIs for model, data, and algorithm. I think I will cover it later. Yeah, so based on this, we designed some work-oriented programming interface. Actually, is a message passing idea. It's not like the distributed training you just do or reduce. So if you are familiar with distributed training, normally you can call some MPI like a distributed or reduced API. By this way, you can collect gradient from different GPUs. But this is not helpful for federated learning because federated learning assumption is that the data is isolated. It's not even in a single cluster, in a single data center. The data distributed everywhere, including your different persons or different organizations in different cities or even different countries want to collaborate. So we prefer another design pattern for it. So this is a key design of federated learning library. So we hope it's a message passing idea, meaning that you can define any kind of message to exchange the gradient weight and even customize your message with other workers. And also you can try to ingest as many message as possible. So by this way, it can customize and support diverse applications because different applications and algorithms may have different message passing. So the training flow may be different. It's not exactly the same as training locally and aggregate globally. So maybe there are other patterns. So that's why we designed it like this. And we further support a trainer there so people can customize the training and try to customize different loss function and maybe use different models. So you can see this API is not that it is the old version, but nowadays we are trying to improve it and make it simpler. Not just trainer, hopefully very soon we will provide APIs for people try to design different aggregator and different client selections. So a lot of customization can be upgraded later to simplify the development. So we haven't developed the APIs a lot in the past 2 years when we do research because we hope researchers can fully focus on the algorithm innovation rather than some software engineering and architecture design, which is not friendly to them. But for production, especially when we are running a company, we hope the library can be unifying the APIs to support diverse industry applications. So that's why we are doing API upgrading. Yeah, so this is the vision. Hopefully we can make the library write once and run everywhere. For example, if you want to run everywhere, meaning that you can just change the backend, just one line code. You just even just change the backend. You can make it happen in such IoT setting from Linux server like Edge server setting. So yeah, so here are some benchmark results. You can read details from our paper. After publication, it gets more than 100. I just checked today, it's about 150 citations and used by a lot of university and companies. Nowadays, today we in our company upgraded into open source community. So you can join our Slack and discuss with us and see the new version of the open source library. And we also make a very comprehensive documentation for you to get quick started. And for ISDK, as I mentioned, the main focus is on Rust and C++ language to improve the efficiency on these edge devices so we can train efficiently, train a larger model with less resource there. So that's a focus on edge ISDK. And we also have a user-friendly MLOps, which try to collect it because you can see in real world, if you want to collaborate with your friends, let's say you have a laptop, your friends have another laptop, each laptop has some personal data. So if you want to collaborate with your friends, the difficulty is that you don't have a server there. So you have to manipulate the server, develop a cloud service, and then do collaboration. So which is a very complex procedure if you want to do federated learning. So our ML platforms to make it zero code, meaning that you can directly register account there and to upload to just log in with just one line login on your laptop, and then you can collaborate. Yeah, so here I just show you a live demo. It's just 1 minute live demo to briefly introduce how our platform, MLOps platform looks like. So this is the UI of our ML platform. Let me show you. So in the homepage, you can see you have your edge device. You can see some groups, and we provide a user guide for people to do the collaboration. So the process is that you first just one line login, meaning that by this login, you install an agent on your smartphones, on your laptop, on your edge server. And then you can just operate using the UI to collaborate with other friends. For example, you want to invite friends and invite collaborator, you just copy this link and send it to your friends. For example, it's very similar like you share a Google Doc to your other collaborator for research. And then we can do some, for example, we can write a paper together. So here we just train a model together. And finally, in the third step, you can decide which model and which task you want to train and just start training. So we make it very simple to use. So it looks like this way. For example, once you invite your collaborator, you can see the collaboration. For example, this demo one and demo account, each one has a Mac OS, so they can train together. This is a diagram to show what the group, what the cluster looks like. For example, here's a hospital and a demo account. They can collaborate to train a model. So by this way, we simplify the real world production a lot. For example, two hospitals want to collaborate, they just log in and share a link, then that's it. They can do the training. And we also try to manage the project, make it simpler. For example, you can customize the model you would like to use. For example, you can customize your source code. You can write different model and you change the path of your data. Or you can even upload some synthetic data to do some research. And then you can turn some hyperparameter here and save the configuration. And then when you start the training, there are some advanced features for you to do some experiment analysis. For example, you can observe the status of each device, and what's the name, and what's the type of OS, and what's the device ID, and some memory resource and cost. And we can also observe the training curves, which is a standard way like TensorFlow and PyTorch. They all provide this solution, but our solution here is the distributed solution, meaning that it can also support some system analysis. For example, here you want to understand federated learning. So what's happened on each device? For example, on this device, it only trains a very short, just less than 1 second. And then it can do aggregation and do communication. For example, here it calls the communication in less than 2 seconds. I think this is a simulation result in our local computer. That's why it's so fast. In practice, we use this figure to help researchers to understand what's happened in each device. For example, maybe some device is a bottleneck. For example, if local training costs a long time, then we can optimize the device or just remove that device from the training. So by this way, we can do some training time monitoring and simplify the development and check the performance bottleneck. As you can see, we can also see some memory and CPU cost on each device. And finally, we provide a model serving, meaning that after finishing the training, you can serve the model on your device. And we are trying to polish the API later, so it's just one API to integrate to your service. And finally, we have some logging, meaning that you can try to check the logs and to see what happened on each device. Especially the logging is the first one, our first system that provided distributed logging, means that you can check log for a specific client. For example, this client 1 means that it's not the entire log from the server side, it's from the client side. So in order to achieve this, we have to upload the log on the fly to the system so that you can observe what's happened there. And you can also check log on the server and all logs. Yeah. So this is the entire system MLOps to simplify the deployment and system optimization and even algorithm optimization in practice, because in practice it's a very complex environment. It's not like a cluster that you can fully control. It's a remote server located in your friend's laptop or your friend's servers. Yeah, so this is the system we're trying to build. So I think I finished the first part of my presentation. So next part, I will introduce some algorithm. So I'll stop here to take some questions. Any question about the system?
Yes, I have some question. First, thank you for such a very nice solution to bridging the gap between research and industry. So I have a question. Does the FedML framework allow us to do some gradient compression to eliminate, to reduce the communication cost? And also, is it flexible enough for me, like as a researcher, to implement some kind of custom training? For example, I want some client to have a backdoor, like a backdoor attack simulation. So is that possible to do with the FedML?
Yeah, very great question. Actually, we met this issue 2 years ago. So in order to solve this kind of problems, the first thing we did 2 years ago is we provide a customized trainer. So you can see in this trainer, you have the train function and test function. And we also input you the model you have, meaning that you can control the model and return back the trained result. Meaning that in this train function, you can do whatever you like, including attack this model and compress this model. And maybe sometimes you have to do some different aggregation on the server side. I think those APIs we will release very soon, but for local training, you can fully customize by this API. I think we already changed the API a lot recently. So if you look at this tutorial, if you look at our repo, actually there are a lot of different sub projects are developed based on FedML core framework. For example, this NACO paper we get accepted recently in NLP community. So FedNLP actually, if you look at the repo, is just based on FedML framework, meaning that in this repo we can customize any kind of model and manipulate the model. And I think the model compression is very natural there. Yeah, I'm not sure whether it answers your question.
Yes, you did. Thank you.
Yeah, if you need such help, just free to contact us by Slack. I think like the new APIs for you to simplify your research. You just focus on this function. You don't need to care about the real-world deployment and a lot of disputed system development. Yeah.
Hey, Chaoyang, Vishnu here. Great presentation so far. Thanks for sharing. So one question is, I did use the demo in the past, right? But is there a way I can know like if a differential privacy is applied when I connect my laptop or mobile devices to the demo? Like unless I go into the code and see, okay, use differential privacy with some epsilon or something, right? How do I know the data I'm going to share is private or maybe it's shared and those kind of?
You mean during the training, how you can know that when you applied differential privacy, you still are not sure whether it's private for your collaborator, right?
Yeah, I haven't tuned the epsilon, right? Depends on how I tune.
Yeah. That's why in our lab we don't follow differential privacy a lot, because in practice, as my experience, especially if you turn the utility, the privacy utility hyperparameters, normally it will downgrade accuracy a lot, right? You have to turn a lot of hyperparameters and finally you find a way, oh,
yep,
this one may make it perfect, right? So that's why I think later I will talk about the algorithm a little bit. So in that algorithm, we call it secure aggregation. So in those algorithms, we never break any hyperparameters. We keep the hyperparameter itself, it's exactly the same, but it still guarantee the privacy of individual model. So by that way, you don't need to turn any hyperparameters. I think that's the benefit. That's why I appreciate secure aggregation rather than differential privacy.
Okay.
Yeah, if you want to differential privacy, recently I've learned from Google researchers that they try to do a concept called verified federated learning, meaning that they want to verify whether they're to evaluate your system to check whether it really can protect your privacy. So that's a problem that people can has to handle in practice, because in practice, let's say you output your product to your customers, your customers may always ask whether your system is private or security. There's some issue there. So normally we just argue we provide this algorithm, but they need a report to show them that, oh, you really make it happen. So verified federated learning, I think is very important for startup. I think it's also very promising research direction. Yeah.
Awesome. Thank you.
Yeah, yeah, especially for AI, if you can see my screen. So for AI this year, especially people try to think about this verifiable federated learning. I think this is very important. Maybe you can follow this workshop to check whether researchers has already tried some ideas there. Yeah.
Cool.
Yep. Yeah, we launched this workshop because this is a real problem in practice. Yeah, you cannot argue with customers saying that you already have DP, you already have segregation, but you have to show the report to them. Yeah. Okay. So now let's move to the algorithm. Yeah, I think I've crossed a lot of time. So maybe in the algorithm level, let me just higher level introduce what I have done. So this is a system for cross-signal disputing and federated learning. So the main motivation is that you can see there are a lot of hyperparameters in a single GPU. So a single GPU can even not hold a giant model. For example, nowadays, if you want to train billion level transformers, normally the way is to do like zero optimization. We try to partition the weight to different GPUs and then do optimizer state so that you don't need to cache a lot of memory. But more, even though people still cannot hold a giant model because the model size is too big. So we have to use model and data parallelism. So as you can see, this all reduced SGD may not be enough for giant model. So in all reduced SGD means that we assume that a single GPU can consume the training, the SGD optimization to get a gradient like the G1, and then synchronize with other GPUs to do aggregation. So I think this is impossible when the model size becomes big because you cannot even get a gradient locally. So in order to solve this problem, people have two lines of ideas. The first one is system-wise optimization, like the model and data partition. So model partition is very easy to understand. You just cut the model into different layers, or for a layer, you cut to different inter or tensors and operators. So by that way, we can put this operator or layers into different GPUs. So you can reduce the memory cost for a single GPU and then accelerate training by using parallel computing. And for data parallelism, I think it's a different idea that we try to split the mini batch into micro batches, or sometimes we consider overlapping different batches. For example, the batch size 1 and the batch 2, we can overlap their communication or computation. And so by this way, we can accelerate the training and even reduce the memory cost. So here is an example about pipelining. So for example, you can partition the model into different GPUs and do forward propagation pass through device 0 to device 3. And then you get loss and do back propagation from the last device and to the first device. So by this way, you can upgrade your gradient. And the idea to reduce the bubble is that if you look at it from time or perspective, it looks like this. So each GPU takes part of the computation to forward and then back propagation and then to update. But the issue of this idea is that it has a lot of bubble, meaning that most of the time the devices are idle. They do not perform any computation. So in order to address this problem further, we split the model, the batch size into micro batch size. So by this way, we can shrink the bubble from the bigger triangle to a smaller triangle. Yeah, and if you understand the pipelining paradigm, we can further make it hybrid to data parallelism, meaning that you can have different GPU cluster in each GPU server. You can do your pipelining, and then cross GPU server, you can do all reduced communication, which we call it data parallelism. So this is a hybrid of data and pipelining parallelism. And based on this system optimization, people also propose some ideas like neural net search, try to search some sparse neural net search, but has more efficiency and high accuracy. And also people think about how to do sparse training, and meaning that although the architecture is there, you can do some pruning or quantization to reduce the memory cost so that we can train another model. And sometimes people think about large batch size training because for bigger batch size, it may not reduce or increase the memory linearly. So by that way, you can train a slightly larger model. So these are the two lines of work. From the system-wise, you can see the benefits that they improve the efficiency and communication. Memory costs a lot, but they never consider the SGD optimization or the model architecture. But on the right side, the machine learning researchers mainly focus on improve the efficiency mathematically, fundamentally, but they may not understand what that system means. So from system perspective, I think the lack of system design to amplify the algorithm benefit. So I think for this research, I want to explore what if we co-design these two, what if we have both expertise from distributed system and machine learning. So this is the first paper that I tried from this direction. And I think this is also the first paper in the previous research that think about distributed training and algorithm co-design. So follow this idea, I start from hybrid pipeline and data parallelism. And then from the algorithm side, I think about progress training. So by this way, we can make the distributed training system as a dynamic elastic training system. So let's see how it looks like. So progress training means that you can train the model layer by layer, meaning that you can first train a few layers and then add an additional few layers and train these additional few layers and again and again. By this way, you can finish the training. On the right side, we call it freeze training. It's also a kind of progress training. This is the motivation observed by a theory paper that you can see the machine learning, the model, especially deep neural network like ResNet, it converts in a pattern that the layers close to the input data converge faster than the layers close to the output. So if you look at the yellow color, means it compares the weight when it start training and the weight when you finish the training. As you can see, as training goes, the first few layers becomes more yellow, meaning that it already converged. As time goes, the layer close to the output becomes converged. So based on this idea, what we can do is to do progress training, meaning that we can free some layers once we finish the first few layers training. So, and then gradually train the later layers, because those layers are already converged, so you don't need to cost energy there. So based on this idea, we plug in this progress training to distributed training system. So by this way, you can see that there are 3 key observations. I think there's a gap between system and the algorithm. So first, as you can see, the computation costs become unbalanced because once you free some layers, so meaning that you don't need to do back propagation for it. So the memory cost is not reduced, and then also the computation cost is reduced. And also for communication cost, you can see for all reduced communication, we don't need to synchronize those layers away to other machines because it's already frozen. So based on this motivation and observations, we can design a system. So we designed to call it as the pipe transformer. So the system is a very interesting system. It's a dynamic system. It's not like static system that you start training and the entire running process, it keeps the same. So in our system, the system resource is dynamic changed, meaning that at first beginning, let's say you have 1 GPU, server 0, which has 8 GPUs, you put the pipeline there. And also the server 1, you put another pipeline there. So as train goes, if you free some layers, meaning that those layers we don't need train, so the memory cost is reduced. So what we can do is to shrink the model. For example, we use R2Pipe to shrink the pipeline from 8 GPUs to just 4 GPUs. And further, we use R2DP, meaning that it can create new data parallel workers. So by this way, you can see we further create this new pipelines here. So this pipelines also only has 4 GPUs in each pipe. But the benefit is that you can see there are 4 data parallel workers. So by this way, it can accelerate the number of data parallelism. So previously, we only have 2 workers work simultaneously. Now we have 4 workers work simultaneously. So as time goes, it can become a pro data parallelism. So let me show you an animation to understand how it works. So first, we have 2 pipelines. One is at server 0, another one is server 1. And then we free some layers. For example, we freeze the transformer models, the first few layers, and then we can shrink the model. We first add 2 additional pipelines and connect the new pipelines with old pipelines with data parallelism, meaning that they can exchange the weight and the gradient with all reduce. And we further shrink the models as we freeze more layers and we add more pipelines. And we further freeze, shrink, add more. So the process is very simple. If you understand the concept, we freeze, we shrink pipelines, we add more pipelines, we freeze, shrink, add, freeze, shrink, add. So it's just repeats this process. So actually, it's a very complex system design that includes 10K lines of source code. We release this at PyTorch blog. So the key result takeaway here is that you can see the throughput of this system. Throughput means how many samples it takes during training per second. So as you can see, the previous system mainly a straight line, meaning that the throughput keeps the same during the training. But our system, you can see the throughput increase gradually, like the blue color shows. As you freeze more layers, the system can adjust, make it dynamic, elastic, so that consume more samples per second. So this is a dynamic system, and it accelerates about 3 times of the training. So this is a pipe transformer research. So now let's switch to, so this is more like cross-silo federated learning, meaning that you have 2 silos, like the bank and hospitals. You want to train a big model, and so you can accelerate training. So there are a lot of extensions people can try to utilize this elastic idea. So the next algorithm I'd like to present is about cross-device. It's like smartphone IoT. So this paper we call group knowledge transfer. So here I just highly briefly introduce what the idea looks like. So the motivation is that you cannot train giant model on Earth devices. So how we can do it? The basic idea is that we formulate as a new problem. As you can see, this diagram, I think this is the key insight. Nowadays, many people are following this direction. It's also a very promising direction. So we are the first paper propose this question for researchers to answer. So you can see federated learning for centralized training, normally we just collect data from Earth devices and in a central server, we train the model. And for federated learning, the idea is that we do not transfer the model to the server side, we just train locally and transmit some models from client to server. So these are two different paradigms to address the real world challenge, but we think about another way. We think of it as a transfer knowledge. Transfer knowledge actually is the idea that you want to transfer knowledge from many small neural network to a larger one. So the larger one has more capacity to obtain high accuracy. Why we want to propose this? Because in real world, we cannot train such a giant transformer model like the pipe transformer idea. Of course, you cannot operate a pipeline on your smartphone, right? So how we can address the smartphone IoT setting? We propose this question. The research question is quite open question. So it's still not perfect, but I'm still searching new ideas to address this problem nowadays. So the formulation is that, let's say you have a lot of small neural network on your smartphone. Let's say your smartphone has enough memory to hold this, let's say CNN, just a few layers of CNN. But you want to get a giant model on your server side to provide a cloud computing service for people to do some model inference. So what if we can transfer knowledge from this small neural network that train locally and to get a giant model on the server side? So by this idea, I think the benefit is very obvious because you don't need too much memory. You don't need a powerful machine on your smartphone. Also for wireless communication, you don't need a very high bandwidth communication. For example, in the pipe transformer idea, you have infinite band to accelerate the training because the infinite band normally has 100 gigabit per second. Such a high bandwidth, even for 6th generation wireless communication cannot achieve. So how we can address this problem? So maybe a small neural network can makes life easier. So that's the formulation. So under this goal, we propose the group knowledge transfer idea. We first cut the model into two parts. One part is the feature extractor. We put it on the client side. Another part is the server side. We put it on the a larger portion of the model. Let's say it has 100 layers, but for feature extractors, the yellow color, it only has a few layers. So by this way, we can collaborative and orchestrating the client training and server training. So the way we do this collaboration is that we try to do some local training by add a small classifier there. So based on this, we can have a compact CNN. For example, we can then train there and transmit the activation map to the server side. So the server side can take this activation map as the feature space and then train on this feature space and then get a optimize this server model. And later you can transfer back to the client side, can further boost the performance. So by this way, our experience show that this way can work in practice and it can largely reduce the memory cost. The main is, so there are a lot of mathematical formulation. I think I can skip it due to the timing limitation. So the formulation, actually, the high-level idea is that it's a bilevel optimization, meaning that we optimize locally for a few rounds and then transmit the optimized result. For example, the activation map to the server side. The server side can continue the optimization. So it's a bilevel oscillating minimization problem. As in practice, there are, so you can see by this way, we can reduce the communication cost a lot. But the future is that we hope to make it more secure, meaning that you transmit activation map, maybe it contains a lot of privacy there. So nowadays people try to make this more private by using some, for example, differential privacy or even security secure aggregation method. So here I just provide you an insight how to do research for resource constraint edge devices. So this is the direction we are still trying to improve it. For example, we try to extend it to transfer models. We try to make it the model architecture heterogeneous, meaning that each client in the future, you can imagine each person has different models, right? Each person has different models. So what if they want to collaborate together? The model architecture is totally different. So how we can do it? I don't think aggregation can help. Only knowledge transfer may be the final solution for it, because you can eachbody can train different model locally and transfer some kinds of knowledge to the global and then get a good performance. So knowledge is not necessary to be activation map. Maybe there are some other ways to do it. Yeah, so this is the second algorithm I want to present. So the third one, I think I can also briefly introduce it. Before starting from this paper, do you have any question for the cross-device and cross-silo setting? Like the smartphones and the GPU servers. Okay, let's continue the third one. So this one is a little bit different from the previous two algorithm research. So you can see the pipe transformer target the cross-silo GPU cluster setting. In cross-device, we target smartphone setting. But both of these settings, we find there's very significant, very serious problem there is that people do not have enough labels. This is a problem that when we try to run the startup, we try to talk with customers. They always ask us, they need to hire a lot of engineers to label the data in centralized setting. But what if we make it federated, meaning that data is isolated to edge devices, how we can label data there? So this is actually a very important problem in federated learning. Nowadays, it becomes a bottleneck if you want to do startup for it. So in order to address this problem, in this research, we explore this idea. We think about how to do self-supervised learning on resource-constrained edge device, and also in some data and system heterogeneous setting. So the idea is that for self-supervised learning, I think you are familiar with it in computer vision and large language processing community, especially for CVPR. People publish a lot of paper in this domain. So the basic idea is that you can train an encoder on some raw data with this self-supervised learning paradigm. So this we call pre-train. Once you finish the pre-training, what you can do is for some downstream tasks. For example, you have a large-scale ImageNet, or even bigger than ImageNet. Let's say you collect all data from a Google image, and then you pre-train the model there, and you get an encoder. The pre-training mainly use, for example, image classification, but you want to do object detection. So what you can do is to directly utilize this pre-trained encoder and add another object detection classifier or some different loss functions. And then you can train on these downstream tasks by utilizing just a few number of samples, then you can get a good performance. So meaning that we have a foundation model which got from self-supervised learning, and then we can fine-tune it on some small-scale dataset with supervised learning. So this is very promising for federated learning because you can see in practice, we already have a lot of public data. So why we not use this public data to get a pre-training model and downgrade that model to federated learning edge devices and then do some fine-tuning for those downstream tasks with private data. So the mixture of public data and private data, and then we can do unsupervised learning there. So this is very promising result we get. So the basic idea is that for this idea is that for self-supervised learning framework, there are dual neural network, meaning that let's say this dog, we try to do some data augmentation, we transform the direction of the image and change the color and texture of this image, and then you can the two encoders and take the different augmentation of this image and then do prediction. So the idea is to try to minimize the similarity between these two. One is from the predictor, another one is from the second encoder. So the intuition here is that the two augmentation are from the same dog, right? So that's why we should minimize the loss function to minimize the distance. So by this way, this optimization method, we can pre-train and get a very good performance encoder. So in order to make this happen, we have to train on very giant model and a very giant huge number of samples. So this is pre-training. And in step-supervised, we try to plug in this framework, the local optimizer to federated learning. The idea is very simple. We just replace the local trainer with this step-supervised learning. And hopefully we can get good results. But luckily, you can see we get very similar results like centralized training. But this is not enough for federated learning, because in federated learning, I just mentioned there's resource constraint problem and data heterogeneous problem. So in order to make it useful for federated learning, we have to make it personalized and resource constraint to address resource constraint problem. So we follow this step-supervised learning framework and further make it as a personalized model and a global model, meaning that in each client, we have a global model and personalized model, and try to minimize their distance, especially the output, to make a constant there. For example, you can minimize the distance between the predictor from the first client personalized model and another global model. And by this way, we can have different ways of minimization. For example, the live way is try to calculate the L2 long to get the regularization of these two models from personalized model and global model. So by this way, we can personalize it. We can also reduce the resource constraint problem, because we can use gradient accumulation. We can train global model and personalized model alternatively. So by this way, we only need to exchange the weight and gradient with other users by using the global model, but keep the private model private. So there are multiple benefits of using this framework. It's unlabeled, and also it reduces the memory issue. It also maybe enhance the privacy because you exchange with global model rather than personalized model. So this is a high-level idea. We try to formalize the formulate it as this optimization problem. And we also compare with other optimization problem. For example, the optimization method, for example, local adaptation and the meta-learning and even bi-level optimization, which I used in FedGKT paper. So all these baseline actually are very strong baseline, but actually our paper, our algorithm beat the baseline not significantly, but for still a large margin. Yeah, so based on this algorithm, we further plug into FedML framework. We haven't open sourced it yet because currently we are reorganizing the source code, especially reorganizing GitHub. So let's hopefully in the next month, we can release this framework for users to try to do some pre-training on the server side to get a giant model and then do some fine-tuning on edge devices. Yeah, so as you can see, the result is very promising. Even in 90s data set, it can still get reasonable accuracy without using labels. And for some baseline, like the bi-level optimization, I think which is very strong baseline. And the memo is also very strong, but we will still beat memo. Memo has the issue that it has to calculate second order, first order different number of gradients. It may cost a lot of memory and computation cost. So training time there is slightly slower. For local adaptation, it can achieve good accuracy at the first phase, but later if you further fine-tune it, it may become worse. So the phenomenon there is very strange, but our algorithm make it stable there. We just use the regularization, which is simple, but it works well in practice. Yeah, we also compare with some ablation study for it. So that's the unsupervised. So maybe in the next few minutes, I can talk a little bit about the skill aggregation I just mentioned. So for skill aggregation, actually the idea proposed by Google a few years ago. At that time, I think there are ways to, they also think about federated learning. At that time, they don't call it federated learning, but they already start to work on it, like skill aggregation for privacy preserving machine learning. So at that age, people call it privacy preserving machine learning. Yeah, but it's in a disputed matter. As you can see here, the idea is very simple. You just try to do some pairwise random, get some pairwise random seeds and do some pseudo code generation. And then we can use this coded result and to mask your model. Once you mask your model, the benefit is that on the server side, you can cancel the masks. For example, if you look at here, the result is still the same, meaning that the server side still can get aggregated model, but the server cannot see your individual model because the individual model is masked by these Z vectors. Yeah, so that's the basic idea of skill aggregation. So in our paper, we further provide a new perspective that we provide a new kinds of coding. Actually, the coding part is not contributed by me. It's contributed by my advisor, Professor Samuel Smith. So he's a information theory guy. He has a strong theory background there. So my contribution in this paper, but I can still introduce this coding here. So we use maximum distance separable coding, and we get this G vector easier than the previous method. And then we synchronize the gradient to the server side. And the benefit of this algorithm is that on the server side, we can tolerate different number of dropout. We can also accelerate the aggregation there. So previous method, they need to do a very complex decoding process there, but our method is just naive aggregation, and we can cancel it. So it makes it linearly speed up compared to existing algorithms. So that's a contribution of this. You can see the complexity is reduced. In our method is reduced to d log n compared to previous method which use n log n or even n squared. So that's the reconstruction complexity is largely reduced at the server side. I think this is very helpful in practice, especially in business world. Let's say you want to serve your Federated customer within a server. If you can reduce the cost on the server side, you can not only accelerate the training for your edge devices, it can also reduce the cost there. You don't need to buy very expensive machine to accelerate training. So that's why this light segregation is very promising in real world. Yeah, so we further improve it with some asynchronous training. Like, for example, we try to overlap the local security part and training part, meaning that you simultaneously can do encoding and training. So that's a parallelism. And we also try to integrate many other communication overlapping technologies here. So this is like a theory and system co-design paper. It costs a lot of engineering resource there. This is also one of the key patterns in our company. Yeah. Okay, so I think I already finished the algorithm present. And finally, I just briefly introduce what FedML can also support in application level, like latent language processing. This is a paper we published in NACO 2022. Yeah. And in this paper, actually, we support not just the task classification, but also including span extraction. For example, you want to get some positive or negative and topic classification for this kind of private message. This is very important in practice because I want to know what I talking in your smartphones, maybe sometimes, but I don't want to see your private message. And also some interesting like the dialogue system, because I want to know what people talk there and what's the whether we can provide a private dialogue system for them. And also, yeah, so this is a latent language processing framework. And also for computer vision, we are collaborating with Konica Minolta, which is a Japanese camera company, but now they extend their camera to hospital setting, meaning that they can provide X-ray sensing technologies, so that hopefully we can help them do not centralize the data from hospital from diverse settings, diverse countries. For example, their devices already deployed to China, to US, to European, and even including United Kingdom. So hopefully we can provide this cross-country federated learning solution for them. Currently, we are still do the POC phase and try to develop a demo based on a few hospitals in Japan to do some X-ray analysis. Yeah, and also for graph neural network, especially for drug discovery and social network domain, which is very helpful. But nowadays, people also made this privacy issue, so that's why they need federated learning. Actually, this is a project that I collaborate with my former colleagues at Tencent. So in Tencent Lab, they mainly focus on drug discovery. So they need drug discovery technologies to accelerate and to make the drug discovery more efficient for some domain expert. Normally, this kind of setting, they require some experiment which is very expensive. So not like computer science experiment just run on computer. They need to do some wet experiments on some chemistry equipment, which is very valuable. That's why I call it commercial interest. So they cannot directly share with other company to accelerate the performance, to boost the performance. So that's why we build such a POC system for them. Yeah, and finally, this is a project we collaborate with DARPA. We want to upgrade your router in 60. Let's say in 60, there's a router which is equipped with federated learning. The router can directly do some outlier detection. They directly train data on this router rather than train on the central server, which is impossible because you see there are tons of routers in the world. You cannot centralize data to the cloud because cloud may be, although storage is very cheap, but when you centralize the data, it may cost a lot of wireless bandwidth. So why not directly train a local model there and collaborate with routers on other cities? So that's the ambitious goal, but it's still doable in our perspective. So currently we already published a FedIoT to demonstrate this concept, but to land it into real world, we also face a lot of problems there, especially in system perspective, how to deploy it, how to manipulate, how to operate it. So that's why we need ML ops kind of platform to simplify the deployment in real world. So hopefully we can bridge the research gap in FedIoT and the real world system for 6G. Yeah, so that's the application level. Yeah, so I think I already finished my technical talk. So finally, this is the final slides of our vision, the vision in our company. Hopefully we can build a community that can connect AI elements, meaning that federated learning is not just for data silos, it can also connect computing resource, for example, your CPU and GPU laptops, and GPU resource, and also including models. Hopefully we can build a community, a marketplace, can help people can train your model, can exchange your model and exchange your data in such a federated, secure manner. So that's our vision. Thank you.
Thank you, Chaoyang. So very, very informative talk.
Yeah, it costs too much
I learned a
time.
lot. And any questions from the audience?
Yes, Professor Chaoyang. So in federated learning setting, the client usually control of the local data and also, if possible, also control of the local training. So if some group of user want to perform a coordinated attack like backdoor attack and then send a poison model to the global server, does that affect the whole server and affect everyone? So is there any defense method that we can help to eliminate such attack?
Yeah, we call this robust federated learning. Actually, we did a lot of research in our lab. It's mainly on my advisor's lab, like Professor Sylvester in USC. Actually, for this direction, I have a collaborator. We put a demo on this FedML framework. It has, let me show you the demo here. So there's a federated robust. Maybe I moved the folder. Let me see. Yeah, there we provide some examples for you to try to do some backdoor attack. Actually, backdoor attack is the first paper published by one of my friends. It's also it's also the open source contributor of FedML. So I'm not sure whether I can find it. Yeah, maybe this one. Yeah, you can see this one. So there's the Earth case black box attack and also some backdoor attacks. So I suggest you to read paper from this researcher. It's called. So now he's a doctor in CMU with Eric Shin. Eric Shin is also doing some machine learning system research. Yeah, he has some famous paper. Yeah, you can see, yes, you can really backdoor federated learning. So it's highly cited paper. I suggest you read this one because you can see it already get 100 citations. This is a strong baseline. And in order to make it robust, I think he also did some research for it, I guess. Yeah, so this algorithm already integrated into, yeah, he's also the contributor of FedML. Yeah, I recommend you to try this paper and to get some related works.
Yeah, thank you.
Mm-hmm.
Other questions? Actually, Chaoyang, I have one question. So here, when you talk about the edge device, you mean it's more kind of the edge GPU or the desktop, or like the mobile phone or the IoT, more embedded IoT devices? Because when we talk, if we consider about the edge training, so we know that if we want to really do some of the training on the mobile phone and or the even MCU, that would be kind of very expensive task.
Yeah. Currently, we haven't tried on some MCU based, but for like essentially in our company, you can see the edge devices. We cover different kind of edge devices, including smartphones, as you mentioned, and GPUs. Actually GPU we also call it edge devices because it's from the perspective of cloud computing. So in cloud computing, let's say AWS, you have a cloud server there, but normally the edge device is located, local trainer located on customers' private server. Let's say you are a hospital, or you are a lab, you have a private server, you want to collaborate with another lab. So we call these two labs machine as edge devices. So this edge device is normally equipped with GPU devices. So it's very powerful. Yeah, so smartphone and GPU devices as two scenarios we target now. And for some industrial settings, we target some powerful edge devices. If you look at NVIDIA Nano, as I guess it's called Nano, I forget the name. Yes, for Nano device, some Nano device even have GPUs. You can see the memory is big, right? So even 4 GB. So this device is, we tried it. We tried even you can train ResNet. So it's not proper, although it's slow, but you can use some efficient like model compression, gradient compression measure, or specification pooling to further make it faster.
Okay, thank you. Thank you very much.
Yeah, because it's based on Linux system, so that's why it's easier. Because for product development, normally we try some standard OS, because all these three kinds of devices based on iOS, Android, Linux, so which make the development much easier.
Okay.
Yeah.
So any other questions from the audience?
So all of this, you have so many students.
Yeah. And also, I have another additional question. So right now, so when we perform such experiment, I think right now we assume, right, that is kind of the device, the communication is via the kind of the line, not the wireless channel, right?
Is for, yeah, you are correct. For smartphones, especially look at the Google scenarios. What I learned from Google engineers is that they only allow 10-minute training for a round. Let's say you train 10 minutes and exchange with other client, but this 10 minutes only happens when users are sleeping. For example, you sleep in the light, your phone is in charge, and also your phone is connected to the Wi-Fi. So when your phone connected to the Wi-Fi, and then for LAN, although it's wireless, but for communication across another smartphone, it's still wired.
Okay, yeah. So actually, that's my question is that. So how about the practical application scenario for federal learning? So it looks like now, so still kind of the more wireline based federal learning is kind of more practical, right?
Yeah. It's, according to our chat with customers, most of the cases are about cross-signal, meaning that you want to, we call it cross-signal, meaning that it's not wireless communication. It's just some server located in different cities or different clouds. That's more easier way to do federal learning, for especially in business domain, because it's just a standardized Linux. You just do a geo-distributed training, then that's it. But for wireless communication, as I mentioned, we need Rust or C++ language to reduce the cost here, and we also rely on the hardware upgrading. But we believe it becomes true later. So nowadays, you can see smartphone is really very powerful. You can train it when people sleep. So it's still not a problem. So that's why we target these easier scenarios. Yeah.
Okay, I see. Thank you.
Yeah. For industry, IoT is also possible because most of the IoT devices are, we do not need to consider the power there because it's charged. For example, smart cameras or some edge server control the smartphone cameras, they are always in charge. So you don't need to care about the battery or energy cost there. So it's just train there because people do not care about the energy cost there.
So we only consider about like the latency and the bandwidth, right? And
Yeah, latency is training time. I think it's always the bottleneck. As for communication, our latest understanding is that communication time only costs 5% of the entire training time. That's a different understanding from academia, because academia, a lot of communication efficient distributed computing or training method there, but actually only contribute 5%. Because in these two scenarios, you can see it's only to cost money for data transfer, because it happened when people in charge and sleep and use the Wi-Fi, because Wi-Fi, you don't need to cost money there, right?
Yeah.
So that's why in practice, I don't think optimize the communication is a good direction. Actually optimize the local computation and memory cost is the correct direction. So that's different from this is also a gap between academia and the research and business work.
That's a very good point.
Yeah.
Okay, so any other questions from audience? So if no more questions, so let's thank our speaker again. So Chaoyang, so thank you very much for giving this talk. I think very informative, very great talk. And also thank all our audience to join our this week talk, and see you next Tuesday. So thank you, Chaoyang.
Thank you. Thank you. Bye.